Hello everyone, welcome to the fourth recitation, and today we're going to be doing chapters. Let me just write it. We're going to be doing, so last time we did chapter 7, 8, 9, so today we'll do chapter 10. We won't be doing chapter 11 today, but we will be doing chapter 10, 12, and 13. Okay, so let's start. Problem 1. This is from chapter 10. Okay. So problem 1 is, let me just draw the figure. Okay. Got it. These are all resistors. Okay. This is point A, and that's visible. Point A, point B, and point C. Okay. And these are the resistors. Okay. So now let's write down the question. The question is, let RAB be the equivalent resistance between points A and B. Okay. Let RBC be the equivalent resistance between points B and C. Now we are given that the equivalent resistance between A and B is 3 ohms. We need to find RBC. Okay, so for such a question that requires you to find equivalent resistance between a segment of the whole circuit is to divide your circuit into the segments that are required of you. Okay, so what I mean by that is, so we are already given the equivalent resistance, which is RAB, right? So let's just draw how that looks like. So let's just assume that this is point A. Okay, so this is point A, and this is point B. Okay, so if you look at the diagram here, let's isolate this and this and draw all in the middle. So you can easily see that we have something like this, right? Which is this one. And then we have 2, 3 here. Okay, so how do we write that? 1, 2, 3. Okay, these are the resistors. Okay. Now, using the series and parallel equivalence, we can write that the equivalent resistance between these points is equal to, so if you look carefully, this resistance and this are in parallel. So how do we write that? We write 1 over AB is equal to, so the top one is 1 over R and the bottom one is 1 over 3R. Why 3R? Because if we just want to find this, we can simply find this as the equivalent. If we just want to find the equivalent resistance between this and this, but only this side, we can just write that the equivalent resistance is R plus R plus R because they're in series, right? So that's how we're writing here 3R. Okay. Now, if you want to find how this looks, so 1 over RAB is 3R plus R over 3R squared, right? Correct. That is 4R over 3R squared, and this makes it 4 over 3R, so that is your RAB, 1 over RAB. Okay, now if you want to isolate RAB, we can just take the reciprocal and we can write 3R over 4. Now, one thing that is already given in the question is the value of RAB. So we can just equate this to 3 ohms, and therefore we get that R is equals to 4 ohms, correct? But that's not where we stop. We need to find this. So let's now draw only the circuit that is concerned with points B and points C. Similarly, like before, let's just draw. So let's just take that this is B and this is C. Okay, so let's see. Let me just copy this here so I don't have to move again and again. Okay, now we've isolated B and C. Okay, so this is B, this is C. Now, how many circuits are on the upper part? 2, right? And similarly, 2 on the bottom. These are the resistors. Now we know the value of R, so simply what we write is, again, 1 over RBC is equal to 1 over 2R plus 1 over 2R is equal to 1 over R, right? How? Because this makes us 2 over 2R. So 2 gets cancelled and we're left with 1 over R. Okay. And we know what R is. So RBC, just take the reciprocal. We get R, which is equal to 4 ohms. So that's the answer. Okay. Okay. So let's move on to problem 2. Okay. Problem 2 is again from chapter 10. Okay. So the problem says the resistance of a wire is 1 ohm. Now, the same wire is stretched to twice its original length, and the radius of the cross section is half of the original. The question is, what is the new resistance. Okay. So that's a pretty straightforward question. I'm going to again ask you to pause, think about it, and see if you were on the right track. Okay. Okay. So now we need to start with writing the formula for the resistance. So if we have a wire, okay, and let's say its length is L, okay, and the radius, and we have radius, so let's just write radius equals R, length equals L. Okay, so that means that resistance we know is rho, which is the cross section, which is the density over the cross section area. Okay, for such a wire, so this is our original. Okay, now it says that we stretched it into twice its length. So after stretching, so this is R prime, which is after stretching. So rho remains the same. The length becomes twice. So now instead of L, we have 2L. And the cross-section area becomes half. So if we can write the cross-section area as pi r square, right? Because that's how the wire looks. Okay. So now it becomes pi r over 2. The radius is half. Okay. And square. So if we take out this expression from here, let's isolate this expression. What I mean is, let's just write rho L over A. Now, what are the extra terms here? We have, and let me write this, pi r square, right? So what are the extra terms here? We have 2 from the 2L, and then we have 1 over 4. So that makes it 8 rho L over pi r square, right? Now this thing is our original R, which means this becomes 8 times R. And what is R? R is 1 ohm. So that means that the new resistance R prime is 8 ohm. Okay, and that's your answer. Okay, so let's move on. Now, the next couple of questions are going to be mixed, so I'm not going to be writing which chapter it is from. But if I see that this is from a particular chapter, I'll just let you know. Okay, so let's move on to problem number 3. So this is from chapter 12. Okay. Yes. So, okay. Now, the problem is a circular coil of wire consisting of 100 turns, each of radius 8.0 centimeters, carries a current of 0.40 ampere. The question is, what is the magnitude of the magnetic field B. So let me just remove the vector sign because I'm only asking you to find the magnitude at the center of the coil. Okay, again, this is a very straightforward question, so I would request you to pause the video, attempt it yourself. And since it's very straightforward, I'm going to leave the redundant calculations to you. Okay, so let's just say, so we're required to find the magnitude of the magnetic field at the center of the coil. Okay, so we have the formula to find the magnetic field, which is mu naught 2 pi Ni over, we have to find the 4 pi r. Why 4 pi r? Because it's usually n, right? So that's the formula. Okay, so now we just substitute the values. And what are the values here? So we are given n, which is 100 turns, so 100. We have the radius, which is 8.0 centimeters, and we have I, which is the current, at 0.40 ampere. So we substitute the values here and find the answer. Okay, pretty straightforward. Moving on. Problem 4. Okay. This is again from chapter 12. Let me check if it's from chapter 12. Yes. That's right. Okay. Okay, yes, this is from chapter 12. What is the magnitude of the magnetic force per unit length on a wire carrying a current of 8 amperes and making an angle of 30 degrees with the direction of a uniform magnetic field of 0.15 Tesla. Okay, so solution. Again, it's a very straightforward question. So like I explained to you that when you're given a couple of things, it's best to write what are you given so that when you write the formula, you can see the things that you have to work with. Okay, so let's just write given. What are we given here? We're given the angle, which is 30 degrees. We have the current, which is 8 amperes, and we have the magnetic field. Okay, it is 0.15 Tesla. Now we need to find the magnitude of the magnetic force. How do we find? We know that F over L is equal to VI sine theta. So now if you just want to isolate F, we can write F equals VI sine theta L. Right? Now we just substitute all the values and get the answer. Pretty straightforward. So let's just do another question from chapter 12. So we have problem 5. So this is from chapter 12. Okay. Good. A toroid has a core which is non-ferromagnetic of inner radius 25 centimeters and outer radius 26 centimeter, around which 3,500 turns of a wire are wound. If the current in the wire is 11 amperes, the question is, what is the magnetic field? Okay. And the places that you need to find the magnetic field is A, what is the magnetic field outside the toroid? B, what is the magnetic field inside the core of the toroid? And C, what is the magnetic field in the empty space surrounded by the toroid? Okay. So the solution. So if you're guessing that the magnetic field outside the toroid should be 0, you're right. This is 0. And if you're thinking that the magnetic field in the empty space surrounded by the toroid is also 0, you're correct. This is also 0. So the only value of the magnetic field that we will get is from here. Okay, so let's just find that. And again, this is very straightforward, and we will use the same formula that we used in here. Okay, so we know this is mu naught Ni over L. Okay, and what are you given? You're given all these things. So let's just write given. We have n equals 3,500. We have inner radius, so let's just take it R1, 25 centimeters, and R2, 26 centimeters. Why will we need that? You'll understand in a second. We have I, which is 11 amperes. Okay, so these are the things that we are given. Now, if you need to find L, you need to consider that we have two radius, okay, R1 and R2. So what will we find here? We first need to find the mean length of the toroid. And how do we find that? So L here is, we know, it's supposed to be 2 pi r, but since we have two radius, what we will do is R1 plus R2 will find a mean over 2. Okay, and that's what will give you L. So you substitute all these and find B. Okay. Okay. So we did problem 5. Let's do problem 6. Okay. And this is from chapter 13. A long solenoid with 15 turns per centimeter has a small loop of area which is 2.0 centimeters square, and that is placed inside the solenoid. Which is normal to the x to whatever axis. You can assume that the solenoid is placed in the y-axis, so then the normal would be either x or z. So just let me just write normal to the axis of the solenoid. You can assume any axis. If the current carried by the solenoid changes steadily from 2.0 ampere to 4.0 ampere in 0.1 second. The question is, what is the induced EMF in the loop while the current is changing? Okay. Okay. So solution. We will again, what are we going to do? We're going to start with given. So what are we given? Let's see. we're given that we have n. We're given that we have n, which is 15 turns. So n equals 15 per centimeter, right? The next thing we have is this a small loop of area this is placed. And now we want to see the change. So change in the current. So delta I, okay, which is 2.0 ampere in 0.1 seconds. Okay, so how are we going to find that? We know the formula for induced EMF, which is E equals delta phi over delta t. Okay, we know what phi is, so phi is BA, okay, which means delta phi is going to be delta BA, right? And what is B? So we have B, now we know already, mu naught n I, okay? So if we want to find delta B, we just simply know that it's the change in I. So you substitute that here, substitute everything here, put this back here, and now you also know the change in temperature, change in time, which is 0.1 second. So at every interval of 0.1 second, we have a change in the current, right? So substituting all the values, what we get, E equals delta B A over delta T, which means delta mu naught NIA over delta T. Now, one thing that you need to understand here is change in phi, if we put delta here, it means that the whole of this is changing, right? So a correct way to put this is, so delta phi means delta BA, okay? And the correct way to move forward is delta B and A as it is. So delta essentially acts as a derivative, right? Plus delta A, B as it is. However, there is no change in delta A. So delta A is equal to 0, which means that we can simply write this as delta B and A as it is. Okay. Similarly, when we put delta B here, the correct way is delta B is equal to delta mu naught N I, right? And if you put the derivative in everywhere, so this is a constant, which means the only two things are delta. In fact, N is also a constant, right? So the only place that the delta goes is I, and rest remains constant, okay? So now we substitute everything here, we get, so let's just put this as aside. Okay. Now we substitute it here. We get E is equal to A mu naught N delta I over delta T. And now you just put in the values. Okay. Okay, so I think we have time for one more question. Let me see what we can do. Okay, let's do another problem. Problem 7 from chapter 13. Okay. Okay, let's do this one. Okay, we are rotating a 1 meter long metallic rod with an angular frequency of 400 radians per second with an axis normal to the rod passing through one end and the other end of the rod is connected with a parallel, oh no, it's a circular, with a circular metallic ring. Okay. There exists a uniform magnetic field of 0.5 Tesla, which is parallel to the axis everywhere. Okay. Find out the EMF induced between the center and the ring. So it looks like a long question. However, again, it's pretty straightforward. So we will again start with the things that are given to us. So we are given the angular frequency, which is 400 radians per second. Okay. And we're given the magnetic field, which is 0.5 Tesla. Okay. Now, it says that one end of the rod will have, so here it says, let's see. So the metallic rod has an angular frequency of 400 radians per second with an axis normal to the rod passing through one end, and the other end of the rod is connected with a circular metallic ring. So this means that one end of the rod will have a zero linear velocity, while the other end will have, so let me just write, one end of the rod will have zero linear velocity, and the other end will have velocity, which is equal to length times the frequency, right? Which means that the average velocity is the velocity at both ends. Since one has L omega. The other has 0. The average velocity comes out to be this. Okay. Now we have to find, and then you just substitute the values here. The other thing we need to find is the EMF induced. So that's given by B, which is the magnetic field, L, and the velocity that we just found. So we get the answer. So we have BL times L W over 2, which is P L square omega over 2. Okay, we just substitute in all the values. In here, so in star, and you'll find the EMF induced. Okay, so that was all for today. And again, if you have any questions, feel free to mail me, and I'll see you in the next recitation class. Okay, bye.